This is a review of converting back and forth from rectangular to polar coordinates. Using radian measure for an angle, convert the rectangular coordinates to polar coordinates. It is important to understand the conversions. The conversions are given by this basic shape: x, y, r, theta. So for example, x squared plus y squared, that equals r squared. So r equals the square root of x squared plus y squared. That would be useful if you had x and y and wanted r, which is what we have here. And then tangent theta equals y over x. These formulas are very useful if you have x and y to find r and theta. We have x and y, rectangular coordinates, and we want to find r and theta. Perfect. Find polar coordinates. So we'll work with these. R equals the square root of 8 squared plus negative 8 squared. That is the square root of 64 plus 64, which is 2 times 64, which is 8 square root of 2. That's R. Without a calculator. Tangent theta equals y, negative 8, over x, 8, it's negative 1, and theta equaling arctangent of negative 1 is negative pi fourths. So our final answer is r theta. So it's 8 square root of 2 comma negative pi fourths. And this completes how you convert rectangular to polar coordinates. Now, since radian measures for angles are not unique, there are an infinite number of possible ways to write this answer. It's worth looking at. So to begin with, where is this point? It's 8, negative 8, so it's down here. 8, negative 8. So this angle, how do we want to measure it? Negative pi fourths is fine. 7 pi fourths would be also acceptable. And negative 9 pi fourths, etc. There's an infinite number. In fact, the answer in the key is the 7 pi fourths. Often books will go with the smallest positive angle, although there are no correct answers unless they specify. And if you go up to the instructions, they do not specify anything about the radian measure. So they could have said something like theta is in between 0 and 2 pi, for example. Then we know we'd have to work with the 7 pi fourths instead of the negative pi fourths. But since they didn't specify that, either of these two answers are fine. Plot the point whose polar coordinates are given. So the radius is negative 2, and the angle is negative 5 pi fourths. Pi fourths are here. I'm going backwards, but that last one's a little bit off. These are where the pi fourths are. So counting positive, it would be 0, 1, 2, 3, 4, 5, 6, 7, 8, etc. Counting negative, well, negative 1, negative 2, negative 3, negative 4, negative 5 pi fourths. So this is the direction they're telling us to face. So we're facing in that direction. That's what the negative 5 pi fourths tells us. We're standing at the origin, facing in that direction. So that's where we're facing. And then it tells us to walk backwards 2 in that direction. So facing in this direction, walking backwards 2 would get us right here. And this would be negative 2 comma negative 5 pi fourths. So when you have a negative radius, you first aim yourself in this direction and then walk backwards. If it's a positive radius, you walk forwards. If it's a negative, you walk backwards. But in all cases, you want to be facing in this direction. So walking forwards would be going there into quadrant 2. Walking backwards would get us into quadrant 4. Convert to rectangular coordinates. Okay. The picture we need for conversions is the x, y, r, theta triangle. Now, sine of theta would be sine SOHCAHTOA, so it's SOH, opposite over hypotenuse. So that gives us y equals r sine theta. Cosine theta is adjacent x over hypotenuse r. That gives us x equals r cosine theta. These two formulas are for converting, if you know r and theta, getting y and x. Well, that's exactly what we asked here. Find rectangular coordinates, and here's r and theta. So, x equals r cosine theta. So that will be r negative 4 cosine negative pi thirds. And from the unit circle, cosine negative pi thirds, that's quadrant 4, where cosine's positive. So we have negative 4 times, and pi thirds, cosine's 1/2. 1/2 of negative 4 is negative 2. X equals negative 2. Y equals r sine theta. So y equals negative 4 sine negative pi thirds. Again, negative pi thirds is in quadrant 4. Sine is negative in quadrant 4, so it's negative 4 times negative, and sine of pi thirds is square root of 3 over 2. So that gives us y equals positive 2 square root 3. So this builds us up to the point x comma y negative 2 comma 2 square root 3. And that is our rectangular coordinates for our polar point. For the given point in rectangular coordinates, find equivalent polar coordinates for r theta for r is greater than 0 and theta is in between 0 and 360 degrees. So let's start off by locating this point. Negative 6, negative 6. Here it is. So that's negative 6, negative 6. R is positive, and theta is in between 0 and 360 degrees. So these are the information pieces we're looking for. Now we have the formulas. R equals the square root of x squared plus y squared. So that'll give us negative 6 squared plus negative 6 squared. That is 36 plus 36, which we can get to 2 times 36, which you can square root 36 and get 6 square root 2. That's r. R is positive. That's what we needed. Positive r. And tangent theta equals y over r. This is our other formula. Y is negative 6, r is negative 6, so that equals 1. So tangent theta equals 1. That gives us theta equals, what could be pi fourths? That would be this angle, but we want this angle. That one's 5 pi fourths. There's an infinite number of answers for tangent theta equals 1. You have to pick the correct one. And I still haven't done this because I'm in radians. They wanted, highlight degrees, 45 degrees. That would be 225 degrees. Okay, 225 degrees. So r theta, 6 square root 2 comma 225 degrees. That is our polar form. Graph the polar equation. R equals 5 plus 5 sine theta. The first thing I'd like to look at is the sine theta. From sine theta, I can see the period is 2 pi. Now for a sine wave, essentially the key points on a sine wave are where it's at the baseline, 3 different spots, where it's at a maximum and minimum. And if you look at this, this divides this period into 4 equal parts. Although these don't look equal because I didn't graph this very well. 4 equal parts. So if we take 2 pi and divided by 4, this will give me the increment that I'm going to plot our theta with. So I'm going to start with 0, and then I'm going to do pi halves, and then I'm going to go 2 pi halves or pi. I'm going to move by pi halves, 1/4 of the period. This will allow me to get all the key points of the sine. So 3 pi halves, and finally 2 pi. These are my values I'm going to use. Okay, let's go down a little bit. There we go. Alright, so plugging these in, taking 0 and plugging it in, we will get 5 plus 5 sine 0, which is just 0 degrees, sorry, which is just 5. Okay, so then at pi halves, sine of pi halves is 1, so 5 plus 5 is 10. And then 5 plus 5 times 0, we're back to 5. And then we're at 5 plus 5 times -1, we're at 0. And then we're at 5 plus 5 times 0, we're back at 5. Okay, great. These are our theta points. So we're going to go in these directions: 0, pi halves, pi, 3 pi halves, and 2 pi. So at 0, we're out at 5. So we're starting here. Aiming in the pi halves direction, we're at 10. Aiming in the pi direction, we're at 5. So we're walking forwards 5. We're aiming in this direction towards this 90 degrees pi. We're going forwards. So even though we're landing at -5, that's xy coordinates. In our theta coordinates, that's theta is pi and r is +5. And then finally, aiming at 3 pi halves, we're at 0. So aiming in that direction, we didn't go anywhere. And then we're back to a full period. At 2 pi, we're back at 5. Now what this thing looks like, starting here, going up, and back, we have this shape. And arrow going that direction is nice, so you can see as theta increases how this is going through. Now if you don't think that that's enough information, you could actually go in between. For example, pi fourths. If I plug in pi fourths, sine of pi fourths is square root of 2 over 2 times 5. 5 square root of 2 over 2, that would be to a calculator. Graph r equals 2 times 1 plus 3 sine theta. So the first thing to do is to take the period of the sine wave, which in this case is 2 pi, and divide that into 4 equal parts. Get us pi halves. This is our spacing for theta. So we're going to start at 0, and then we're going to go by pi halves. Pi halves, and then pi, and then 3 pi halves, and then 2 pi. If we need more information, we'll go in between, like pi fourths or pi thirds, pi sixths, etc. And now we just plug these values in. 0. Sine of 0 is 0, times 3 is 0, plus 1 is 1, times 2 is 2. So this one gives us 2. Let's try that again. 2 times 1 plus 3 times 0, which is just 2. At pi halves, sine of pi halves is 1. So let's see, 3 plus 1 is 4, times 2 is 8. At pi, we're back to 2. At 3 pi halves, 3 pi halves sine is -1, times 3 is -3, plus 1 is -2, times 2 is -4. Then we're back to 2. You'll notice patterns here: 2, 8, 2, -4, 2, 8, 2, -4, 2, etc. Because we're being very careful about which values we choose here by doing 1/4 of the period. Alright, let's see these points. We have facing in the 0 direction, we're out positive 2. So facing in the 0 direction, walk out 2 when we get to here. Facing in the pi halves direction, we walk out 8. Gives us here. Okay, facing in the pi direction, we're at 2. Facing in this direction, we walk out 2. Now, facing in the 3 pi halves direction, we're walking negative 4. So we're facing in this direction, but we're walking negative 4 and we get to here. Okay, that is definitely a different looking graph. So to complete this picture, we start here and we go out to there and back, and then we do a little inner loop. And that's what happens when you have a negative radius. You get an inner loop. And this should be more circular. Should probably be more circular like this. And that didn't look very good either. Let's try that one more time. That's probably the best graph I'm going to get with my crude implementation. Alright, but this is great, easy to graph if you follow this basic principle. Find the period, 2 pi, divide by 4, and use those equal spacings. Graph r equals 4 minus cosine theta. We will start with the period of cosine theta, that is 2 pi. We'll divide this into 4 to get the key points, spacing, and that's pi halves. So on our theta, we want to go by 0 and then pi halves, and increase by pi halves to pi, and then to 3 pi halves, and then 2 pi. This will give us the easiest points for graphing. Starting with 0, plugging in 0 into cosine. Cosine of 0 is 1. 4 minus 1. So we'll get 4 minus 1 is 3. Then cosine goes to 0, so that would be 4 minus 0 is 4. Then it's at negative 1. 4 minus negative 1 is 5. Then it's at 0. 4 minus 0 is 1. And then it's at 1. 4 minus 1 is 3. So we are starting at, in the 0 direction, walk out 3, getting us here. Then in the pi halves direction, walk out 4, getting us here. In the pi direction, walk out 5, get us here. In the 3 pi halves direction, walk out 4. And then in the 2 pi direction, walk out 3. And we actually end up with a circle. And the center would be right here. So that should be a perfect circle. Great. We're going in this direction. Graph. R equals 5 sine 3 theta. First thing we're going to do is work with the period. The period for sine 3 theta is 2 pi thirds. We're going to divide that by 4. It's easier to multiply by 1/4. And reduce, and this gives us pi sixths. This is the equal spacing that we're going to use for theta. So we'll start at 0, and then pi sixths, and then 2 pi sixths, which would be pi thirds, and then 3 pi sixths, which would be pi halves, and then 4 pi sixths, which would be 2 pi thirds. And at that point in time, we've got a full period. There's always going to be 5 when you do it this way. Dividing by 4, starting at 0, you'll get 5 equal spots, all equally spaced. And this will allow this sine 3 theta to complete one full period. At that point in time, hopefully we've seen a pattern and we can finish our graph. Let's find out. Plugging in 0, sine of 3 times 0 is 0. Sine of 0 is 0. 5 times 0 is 0. So we get 5 times 0 is 0. At pi sixths, Pi 6 times 3 pi is pi halves. Sine of pi halves is 1, so we have 5 times 1 is 5. Pi thirds times 3 is pi. Sine of pi is 0, so 5 times 0 is 0. Pi halves times 3 is 3 pi halves. Sine of 3 pi halves is negative 1. 5 times negative 1 is negative 5. And finally, 2 pi thirds times 3 is 2 pi. Sine of 2 pi is 0. Oops. So by choosing these very carefully, by getting the period, which is normally 2 pi, but it's in general 2 pi divided by this coefficient, 2 pi thirds, and then doing 1/4 or dividing that into 4 parts, gives us the equal spacing. When we use these equal spacings, the sine part, or if you're working with cosine, will do this key value, 0, 1, 0, -1, 0. It makes this problem very much easier to work out. All right, now the directions, the pi 6 directions, pi 6, pi thirds, pi 6, pi thirds, pi halves, 2 pi 6. So I'm doing basically dividing each quadrant into 3 equal parts. These are the directions we're going to be facing as we walk through this. So starting in 0, facing in the 0 direction, don't walk at all. So we start at the origin. Facing in the pi 6 direction, walk out 5. So that'll get us walking out 5 right there. So we're going from here to there. Okay, in that direction. So far so good. In the pi thirds direction, don't walk out at all. We're back to the origin. So we must have looped back around. So we're now at the origin. In the pi halves direction, walk backwards 5. Facing that way, walking backwards would get us here. So we're coming around and we've gone to there. Okay. In the 2 pi thirds direction, don't walk at all, back to the origin. Alright, so we're not quite done. Let's continue on in this pattern. 2 pi thirds, 4 pi 6, plus 1 is 5 pi 6. And then 6 pi 6 is pi. Continuing on, look at our pattern, 0, 1, 0, -1, 0, 1, 0, etc. This is an easy pattern. You could also just plug stuff in. So this gets us in the 5 pi 6 direction. Walk out 5, gets us to here. So that's going to be, something like that. Let's try that again. There we go. And then in the pi direction, don't walk out at all, so we're back to 0. And now we have, although this went a little too far out, we have a complete picture. This is now going to repeat itself, so it goes over and over and over and over forever in that direction. And what you'll notice, there are some patterns. If this is an odd number like the 3 or 5 or 7 or just 1, that's how many petals you're going to have. If this is an even number, had it been 4, we would actually end up with 8 petals. It doubles. When it's an even number, you get double that many. When if it's an odd number, you get that many. And still, the basic pattern is find the period, 2 pi thirds, divide it into 4 parts, reduce pi 6, go by equal spacings of pi 6, and you get all the key values that you need. Graph r squared equals 22 cosine 3 theta. We start with the 3 theta and find the period of this cosine. The period is 2 pi divided by the coefficient 3. And we're going to do 1/4 of that, so multiply by 1/4, and that gives us pi 6. So this gives us the theta values to find r. So we're going to start with 0, and then pi 6, then 2 pi 6, 3 pi 6. 2 pi 6 reduces to pi thirds, 3 pi 6 is pi halves, 4 pi 6 is 2 pi thirds. And that completes one period. That may well be enough. So we'll stop there. If we need more, we'll get more. Alright, and now we plug this in. 0, we plug it in for cosine. Cosine at 0 is 1. So we have cosine of 1 times 22 is 22. We have r squared equals 22 times 1. So that's r equals plus or minus square root 22. Well, that's two answers. That's fine. Let's continue on. Pi 6 times 3 is pi halves. Cosine of pi halves is 0. So we have r squared equals 22 times 0, which is r equals 0. Plus or minus 0, there's still just 0. Pi thirds times 3 is pi. Cosine of pi is negative 1. So we have r squared equals 22 times negative 1. R squared can't equal negative 22. So that one actually gives us no information. Interesting. Pi halves times 3. 3 pi halves, cosine. Look at our pattern. 1, 0, negative 1, 0, 1. Easy pattern. So this will be 0 again. R squared equals 22 times 0. That is 0. Here, okay, 0 for r. R squared is 0, so r is 0 as well. Finally, 2 pi thirds times 3 is 2 pi. Cosine of 2 pi is 1. So we're back to r squared equals 22 times 1, giving us r equals plus or minus square root 22. Let's see if this is enough information for us to go on. It might not be. In the 0 direction, we go out square root of 22, which is a little less than 5, a little more than 4. But in both directions, we walk forward and backwards because r squared equals 22, so r is plus or minus. So we're going to walk forwards and backwards. We're going to get to here and also here. We're starting in two different spots. Okay. Now in the pi 6 direction, which is in this direction, we're out 0. So we've gone from there to there, but we've also gone from there to there at the same time. This is moving in two different directions right now because it started in two different spots. Crazy. Oops. There we go. Let's see. Pi thirds in this direction. It doesn't even exist. All right. And now, pi halves, we're at 0 again. So we just appeared. It's kind of a crazy graph. So we've gone from here, and then we disappeared. Went into the complex plane between pi 6 and pi thirds, and then pi halves, we're back to 0. So this whole time it was in the complex plane, no graph. And then all of a sudden it's back to here. Then in 2 pi thirds, which is in this direction, we're back plus or minus square root of 22. So we're here, and we're also here. Now this isn't necessarily enough information to go on yet. So we're going to need some more increments of our pi 6. 2 pi thirds, 4 pi 6, 5 pi 6, 6 pi 6 is pi, 7 pi 6, 8 pi 6 is 4 pi thirds, 9 pi 6 is 3 pi halves. I don't know how far we need to go. The pattern's going to be easy though. Notice the pattern. Plus or minus square root of 22, 0. Undefined, 0. Plus or minus square root of 22, 0. Undefined, 0. Plus or minus square root of 22. Okay. So notice our 4 pi thirds. This is right here. this direction. We're also plus or minus square root of 22, so we're here and we're here. So we have a six-leafed shape appearing out of this. And we know it keeps going to 0. So it starts here and then it's to 0. And then it goes undefined. Then it's back at 0. And then it goes out to here and then it's 0. So when it goes out to here and 0, it's doing a full loop. So from here to here, it's doing a full loop, backwards and forwards. Undefined, then it's back to 0. So it goes there, undefined, then it's back to 0. Square root of 22, over and over and over. So this was definitely one of the harder ones. What's interesting about this, you would expect to get 3 leaves out of a cosine 3 theta. Because of the squared, it gets doubled because you get 2 solutions every time. So you get double leaves. So it's basically a 3-leaf clover, but it's been doubled. So you end up with 6 leaves. Okay, moving on. For the given polar equation, write an equivalent rectangular equation. R equals 10 sine theta. Well, R equals the square root of x squared plus y squared. R squared is also very useful. That's x squared plus y squared. X equals r cosine theta. Y equals r sine theta. We just have sine theta. We don't have r sine theta. So the key to this problem is multiplying by r. This gives us r times r squared equals 10 r sine theta. So we introduce an r so that we have perfect substitution for the y. And we also happen to have nice substitution for the x squared plus y squared. Great. So r squared, x squared plus y squared equals 10 r sine theta, y. And that's it. This one really is a simple trick. And that is, you want to make a perfect substitution. So if you have a cosine theta, you're going to want to multiply by r to get a perfect x out of it. If you have a sine theta, you're going to want to multiply by r to get a perfect y out of it. And the benefit also often makes r squared, which keeps you out of square roots. Great. Convert to rectangular coordinates. R equals 1 plus 2 sine theta. So we have a sine theta, but we don't want a sine theta, we want an r sine theta. So we're going to multiply the left and the right side by r. This is going to give us r squared equals, and we'll have to distribute this r through, r plus 2r sine theta. The point of doing this is to get the r sine theta. Y equals r sine theta. So by putting that r in front of the sine theta, this piece turns into just y. So we have plus 2y. Now r is the square root of x squared plus y squared, and r squared is x squared plus y squared. So we have x squared plus y squared equals r, square root of x squared plus y squared, plus 2y. So by multiplying by r, we made a nice y substitution. We made a nice x squared plus y squared. We made a little mess there, but it's still an easy substitution. Okay, great. For the given rectangular equation, write an equivalent polar equation. We have x equals r cosine theta, and y equals r sine theta. So we just substitute those in. So y will be r sine theta equals x, which is r cosine theta. And that would work. You usually try to solve for r. So if we were to solve for r, we'd start by getting it on one side, and we could factor the r out. This has two solutions, either r equals 0 or sine theta equals cosine theta. Now r equals 0 is just the origin. this is a whole line. This is not just the origin, so that's not enough. This is sine theta equals cosine theta, and that happens every 45-degree angle, and also in the third quadrant where sine and cosine are both negative. So this is the same as this, and that would be our final answer in simplified form. If you divide it by cosine, you would get sine theta over cosine theta equals 1, or tangent theta equals 1, which is theta equals 45 degrees plus k times 180 degrees. And that is here and here. That's the line y equals x. Perfect. So we can see by doing just a little bit more work that this is in fact true. On the other hand, you wouldn't have to do that extra work. That just makes you feel good, gives you a little better understanding. So this is sine theta equals cosine theta, tangent theta equals 1, theta equals 45, and all of these are equivalent to the original. Convert to polar coordinates. X squared minus y squared equals 4. Now we have x equals r cosine theta. So x squared would be r squared cosine squared theta. And y equals r sine theta. So y squared would be r squared sine squared theta. Pretty basic there. We plug those in. So instead of x squared minus y squared, we have r squared cosine squared theta minus r squared sine squared theta equals 4. And we can factor out the r squared. Very much like rectangular coordinates, in function notation you try to solve for solve for y to get f of x equals. In polar coordinates you try to solve for r. So that's why these extra steps are there. But wait, cosine squared minus sine squared is no more than cosine 2 theta. Not squared, now double angle formula. It's 4. And that's as far as the book took it. At least the answer in the back, and that's fine. You could solve for r squared. You'd be dividing by cosine 2 theta, and that could be dividing by 0 a whole bunch of times, so you probably wouldn't take that step. Convert to polar coordinates. X, y equals 1. We have x equals r cosine theta, and we have y equals r sine theta. So we plug these in for x and y, and we get r cosine theta times r sine theta equals 1. This is r squared sine theta cosine theta equals 1. Looking good. However, there's an identity. If I multiplied by 2 sine theta cosine theta, that's sine 2 theta. I'd much rather work with one sine than a sine and a cosine. I would stop here. It's not a bad problem to work with. We've graphed things like that. This is not too bad to do. Okay, great.